All right, welcome back. So for the second talk, we have Lukas Schoug from KTH, who's going to talk us about multiple SLEs, Gaussian free fields, and fusion. It's yours.
Okay, thank you for the introduction and for having me here. So I'm going to talk now about, it's actually more of a byproduct of a work with Alex Karjula and Evelina Peltola, which with some luck will be on archive Monday or Tuesday. So let's see, how do I, okay. So the outline is the following. I will briefly introduce Schramm-Loewner evolution, and then explain what is multiple SLE. And then, well, the proofs might not actually be properly covered to any degree, but then I will explain somehow how we can use the Gaussian free field to construct multiple SLEs in a bigger class than previously possible. So, as I assume or hope, most of you have at some point heard about the Schramm-Loewner evolution. So this is a family of random planar fractal curves. They show up in two-dimensional statistical mechanics models. They were defined by Schramm, 27 years ago. And turns out to be a very important model. The analysis of these models have been awarded with 2 Fields medals, so it's fairly popular. They exhibit quite interesting phases. So there is one parameter that parameterizes this family of curves, which is this kappa, which is non-positive. And if we pick kappa to be between 0 up to and including 4, then we get a simple curve, like in these two. Well, it's supposed to be simple here. It's just very close to hitting itself. And if we pick kappa between 4 and 8, then we get something which is self-intersecting and which also intersects the boundary of the domain in which it's defined. And if kappa is bigger than or equal to 8, then it's space filling and it hits every single point in the domain. And these curves, they are conformally invariant in the sense that we just define them in one reference domain, typically the upper half plane, and then the law of an SLE in any other domain is just the conformal image of the one in the upper half plane into any other simply connected domain, which we know we can always find by the Riemann mapping theorem. But how do we actually define these things? So we start with this differential equation, which is called the Loewner differential equation. And so this is a way to encode families of compact sets that grow in the upper half plane by virtue of, typically continuous function, Wt. And in order to get an SLE, then we pick Wt to be square root of kappa times the standard Brownian motion. And then we solve this equation, and what we get is, can I move this? What we then get is a family of conformal maps. So we solve it for all z and for all t possible. For some of the points, this won't be solved. This won't the solution won't exist for all times because this denominator can be 0. But this set of points for which the denominator is actually 0 at some point is the interesting set. So these conformal maps, they map a subset of the upper half plane back into the upper half plane, and the complement of the domain of the function turns out to be the SLE curve. Whenever we pick kappa to be at most 4. It's a little bit more complicated if you pick kappa bigger than 4. Not much, but and then this set for which the for which the solution does not exist beyond time t, that turns out to be a simple curve then, and this is the so-called SLE kappa curve run up until time t. So, and this, here you see this conformal map. It maps out the first s units of time for this curve, map them to the boundary, and then the rest of the curve which follows is still a curve here in the upper half plane. And these satisfy normalization so that they look like identity at infinity. And well, I mean, this turns out to be a very interesting family of curves. Not entirely easy to analyze always, but we use a lot of complex analysis tools to deal with these things, and we're interested in the fractal geometry of these. So, for example, if you pick an SLE kappa, then the Hausdorff dimension of that is almost surely 1 plus kappa over 8, if kappa is between 0 and 8. So, and well, they arise somehow as the scaling limits of models from statistical mechanics. So if you look at, for example, interfaces in percolation or in the Ising model, then they will converge as you shrink the as you shrink the grid size. They will converge to SLE type curves. So that was a very brief intro to SLE. And then the question is, what is multiple SLE? Well, multiple SLE is, as the name suggests, a model of many SLE curves at the same time in the same domain. It's been investigated by many people, among the ones listed here, certainly more people. And typically we call n SLE kappa a model of n different SLE kappa type curves. And then the question is, what would be nice properties for these curves to satisfy? Well, a natural one is, in view of just ordinary SLE, is the conformal invariance. So that we should just be able to define it in some reference domain, which turns out to be the upper half plane here, also by virtue of this Levno differential equation. And then conformally map it to any other domain. And there should also be a commutation relation, so that if you have this family of n different SLE curves, it should not matter in which order you actually sample the curves, you should get the same law anyway. And this commutation relation, it's something highly non-trivial. It's certainly not easy to find which curves should satisfy this and locally look like SLE curves. Because somehow the most natural way to try, a natural thing to try is just to say that, well, we have this domain with these 4 marked points. We want to sample one curve between the 2 left points and one curve between the 2 right points. If we start by just sampling an SLE from the between these 2 left points in this domain, and then we sample the second curve, then the law of the second curve will be an SLE in the reduced domain. So it will be an SLE that in the domain that lies to the left of the red part. Whereas if you then start immediately by sampling the blue curve instead, and afterwards sample the red curve, then the blue curve will be an SLE in this domain here. But the red curve will be an SLE in the domain to the left of this. And these laws don't commute at all. I mean, unless you decide to sample them independently of each other, but then they will cross, and that's not what we want from a multiple SLE. So we want them to be non-crossing. So some notation that we will need here is the notion of a link pattern. So we pick 2 endpoints, and we designate in each pair here, we designate 2 points which should be paired together, so that we should be able to draw a link between them. And when considering these points on the real line, then any 2 points in these pairs should be connected by an arc in the upper half plane in a way so that no two arcs cross each other. So this puts quite a restriction on the link patterns. So for example, if you take a square, you take the opposite, you take the corners to be the points that you want to link together. You take the opposite corners and try to link them. That doesn't work because the curves have to cross. So in the context of multiple SLE, a link pattern is there to tell you which points should be connected by SLE type curves. And here, an important restriction is that all marked point must be distinct. So here's an illustration of a link pattern. So this is something we allow. This is 1.1 goes to 0.12, 2 to 7, 3 to 6, 4 to 5, 8 to 11, and 9 to 10. So this is in LP6. And now I'm going to list 4 properties which you really don't need to care about, but they're necessary to somehow to characterize these functions that are necessary to construct these multiple SLEs. So first we fix kappa between 0 and 6. And here it's a restriction on the values of kappa that we can choose because, well, as kappa is bigger, the curves get rougher. And if, for example, if you were to pick some space filling kappa, so SLE for space filling parameters, then you would it's an issue of sampling 2 of these curves because since they are space filling, if you sample one of them first, then you will know the exact law of the rest. So it's the model kind of breaks down there. So we can pick kappa to be at most 6, and then we pick some exponent here. You will see what that will mean, and then we pick alpha in these link patterns, and we consider a function on these ordered 2n tuples in the real line, and this should be a function then that maps this to a positive real number. Then we have the property PDE, which is that, well, this PDE is satisfied by the function. And we have this conformal covariance property, which says that this Z alpha, if we replace x1 through x2n by phi of x1 through phi of x2n, then we get the same thing if we also multiply by these by the derivative of the conformal map at these marked points, and take the exponent to be this chosen h. This is a kind of natural condition to have in conformal geometry. We often deal with structures which, if they're not conformally invariant, then at least changing domains only perturbs things locally. And then we have here an asymptotic for the function, so that if we pick 2 points which are linked together and which lie next to each other on the real line, and we send these points together, then we should have this blow up. So it should blow up as the distance between these 2 points to the power of 1 over 2h. And when taking this normalization, well, of course, if the points are not linked together in the link pattern, then we should get 0. And if they are linked together, this should reduce to a function z alpha hat of 2n minus 2 coordinates, and where this alpha hat is the link pattern that you get by just removing the link pattern, removing the link j to j plus 1. So this is a way somehow to shrink one link into nothing to get a link pattern with fewer links. And then we have this bound in terms of powers. It's nothing you actually need to care about, but it's just something that I should mention. So we say that the multiple SLE kappa partition functions are the collections of these functions z alpha that satisfy the properties PD and COV. We said that the pure partition functions are the ones that, in addition to PD and COV, also satisfy the asymptotic. And these pure multiple SLE kappa partition functions, they are unique recursive collections of functions on these LP of n, which satisfy PD, COV, ASI, and the bound. And so you recall here that this property of the asymptotics that gives us a way to somehow transfer the functions between these link patterns, so that it really preserves a relation between different sizes of link patterns. And this uniqueness is due to Evelina Peltola and Hao Wu, who have done a lot of work on multiple SLEs. So they will be cited in most places where there's something relevant. So now we get to why I actually listed these axioms and want the notion of a pure partition function for SLE kappa. Because if we fix point x1 through x2n, then the curve that grows from xj in a multiple SLE kappa is generated by, so we want to construct a multiple SLE kappa with these points x1 through x2n, and we want it to have this link pattern alpha. Then, in order to generate the curve from the point xj, we again solve the Löwner differential equation up here. But instead of having square root of kappa times the Brownian motion, we choose to pick the solution to this system of stochastic differential equations. So we still have this square root of kappa times the Brownian motion. This is what locally determines the geometry of the curve. That it gives the regularity, and it tells you that this is something very fractal. So this is what makes sure that the curve still has the same Hausdorff dimension, and blah, blah, blah. And this second term here, that's where we throw in the partition function. And this together with the evolution of all the points here, that makes sure that the curve ends up, it finishes at the right point. And here, this VT, they're just the evolution under this Löwner differential equation, or these Löwner maps of the marked points, which are not the chosen one, xj. And this is called the local multiple SLE. This is because this is somehow, it's a very local construction. This tells you how to grow one of these curves, and one can check that this curve actually ends up in the right place. But there is another way also to construct these, to construct multiple SLEs, which a priori is not obviously the same thing. One can show that it is, but a priori it's not obvious. And for this, we first look at this picture. So we have these four curves: eta 1, eta 2, eta 3, and eta 4. We want to look here at eta 3. And And we want to say, so we want to characterize then multiple SLE by the conditional law of each curve. So we say here that D3 is the domain in the complement of all of these curves. If we ignore eta 3 here and we look at all of the other curves, then D3 is the complement of all of the other curves, the component in the complement of the other curves, which contains eta 3. And a property which is called the resampling property is that if we have a collection of curves like the previous ones, then we say that it satisfies the resampling property here if eta 3 is an SLE, if conditional on the other curves, eta 3 is an SLE between those 2 points. And this should hold for all of the curves. So that if you look at D2, which is the domain which is between eta 1 and eta 3, then conditional on eta 1, eta 3, and eta 4, the distribution of eta 2 should be that of an SLE between those 2 marked points. And then that similar things should happen, should hold for the other curves. So if this so-called resampling property holds, then we say that this family of curves is called a global multiple SLE. Here we call it global because we don't look at how it grows locally. We just look at the final picture and evaluate the curves there. See, okay, so does this look like it has the right law if we just zoom out and look at the finished picture? Clearly also a very reasonable notion of multiple SLE. But the question is, does this correspond to local multiple SLE? And it turns out that yes, global multiple SLEs are also local multiple SLEs. Another result by Peltola and Wu. And well, it should be said that often these multiple SLEs are studied as scaling limits of interfaces in statistical mechanics models, such as the Ising model. And quite often, at least at the early stages of multiple SLE, you can see that several of the results at the time only were known to be true in the special values of kappa where we had this convergence from the discrete models. So that was an important tool in studying these things. And then there's a program initiated by Vlad Margarint that seeks to understand and develop the connections between multiple SLE and random matrix theory. And I believe I saw Vlad earlier in the audience here, so now he will feel some pressure to do these things. Right. So now I should get on to the things that we did. And for this, we just need some combinatorial notation. It's a vector of balances. So you pick a vector of p non-negative, p positive integers. You set n to be half of the sum of these values. And then we define some sigma valence link pattern. And don't worry too much about the definition of this. This is only a generalization of link patterns where several links can start at the same point or several links can end at the same point. And the number of curves which grow out of a point or terminate in a point are determined by bar sigma here, so that the point xj has exactly sj curves coming into it or leaving it. And if we choose these link patterns LP sigma, then, well, of course, then for a subset of these called the PLP, there exists a unique law, alpha SLE4, on curves which has the link pattern alpha, which satisfy the resampling property. So this here is the existence of a global multiple SLE with these more general link patterns. And we also have a local description of these curves. So it turns out that these are both local and global multiple SLEs in a setting which is more general than before. And in general, it should be said that PLP is not equal to LP. I will show you an example later. And we need both the global and the local description to prove the uniqueness of the law. And a very instrumental part of it is that we are able to couple these curves with a Gaussian free field, which is important both in constructing the curves and deducing the proofs. So in the last few minutes, I'm just going to tell you somehow about the main features that go into and the main features of the Gaussian free field, which we can use to construct these multiple SLE. So the Gaussian free field, it's some random field. It's a distribution valued random variable. So say a generalized Schwartz function. You can think of it as the two-dimensional time version of a Brownian motion. And it's something very important to people that do various things in probability. So you can relate it to SLEs. You can relate it to diagram models, to characteristic polynomials of random matrices. You can use it to build quantum gravity and conformal field theory. So overall, it's a very nice object. And more precisely, the zero boundary GFF on a domain U is just the random distribution, such that if you test this against a function f, then it's a centered Gaussian, and it has this covariance structure here. So that if you test, if you look at phi tested against f and phi tested against g, then their covariance is given by the integral of f and g against the Dirichlet-Green's function. And if you want a GFF with a particular boundary data f, then you just add a harmonic function with said boundary data to it. It also satisfies a nice conformal invariance property, so that the image of a zero boundary GFF under a conformal map is just a zero boundary GFF in another domain. And it satisfies a nice Markov property, which tells us that if you look at any open part of any open subset of the domain, inside you can decompose the GFF as a zero boundary GFF inside said domain and a harmonic function, and these two are actually independent. So this is a very nice and strong Markov property. Most importantly for us, these GFFs can be used to find SLE4 type curves, which will be coupled as level lines. And when you couple these SLE type curves as level lines, you have the following properties: that these level lines are completely determined by the GFF. The boundary data of the GFF, that determines the law of the level lines. And if you look outside of, if you look at what the GFF looks like outside of the level lines, then you again see a zero boundary GFF plus a harmonic function. And here you can see a simulation of an SLE4, which is coupled with a Gaussian free field. So the black curve here is an SLE4. So it's a simple curve that almost hits itself, essentially everywhere. And this property here, that the level lines are determined by the GFF, that's very important, because that means that two curves are, given the GFF, they are independent. So it doesn't matter in which order you sample them, which is beneficial when we think of the multiple SLEs that should have this commutation relation. So our setting is then that we fix some boundary points, and we just fix some bounded harmonic function which has this boundary data. So it's piecewise constant. And we pick phi to be a zero boundary GFF, and we add to it this harmonic function. And we look at a collection of level lines, which are the level lines of odd integer multiple of lambda height. You don't need to worry about what that means. And this is a set of curves which they have a random link pattern. So we don't know until we've explored them completely where these curves actually end up. But what we do know is that if u beta has a jump which is more than 2 lambda, then this allows for two curves to grow from that very point. And the alternating case where beta is just 0, 1, 0, 1, 0, 1, blah, blah, that was investigated by Peltola and Wu and proved to correspond to a multiple SLE4 in the nicer setting. I feel that I'm very much running out of time, but I just have 2 more slides or something like that that I want to cover. So here is a boundary data. And in this case, you see all of the red curves here. So whenever you have a positive jump, that allows one curve to start. And here you have a jump of 4 lambda. That means that 2 curves can start from here. And then whenever you have a negative jump, that's where a curve is allowed to terminate. And somehow the boundary values. So if this has boundary values 2 to the left and 2 lambda to the left and 4 lambda to the right, it can only terminate somewhere where the boundary data then to the right of the termination points is at least 2 lambda and to the left is at most 4 lambda. So it can terminate in this point, for example, but it cannot terminate in this point. So the GFF naturally puts quite a bit of a restriction on where level lines can end, and this is also what somehow limits the number of the collection of link patterns for which we can construct these multiple SLE. So here is an example of a possible realization of this LL beta odd. If you just imagine that this has Hausdorff dimension 3 over 2 instead of being something smooth. Right, and here is an example of a link pattern which is not in PLP for this var sigma 222, because if this here is a positive jump and this here is a negative jump, then this has to connect with a negative jump, and this going backwards here has to connect with a positive jump. And that's not possible for this because this can't be both a positive and a negative jump. So this link pattern does not show up in the allowed models that we have constructed. So yes, just 20 seconds left. So the strategy then is first to check that all of these curves actually satisfy the resampling property. And then we derive the local representation. So we recognize that from the coupling with the GFF, we know the law of one single curve. And we can see that corresponds to somehow the right, we can see that corresponds to the right choice of one curve in a local multiple SLE. And then given this, we can see that that if we know if we know where this curve ends, then it doesn't really the law of that curve doesn't really depend on the underlying boundary data as long as that is an allowed configuration. And then we show that any family that satisfies the resampling property can be coupled with a GFF, so that it is this collection of level lines. So together, these step B and C produce the uniqueness. And well, step A proves that it actually is a global multiple SLE. And yeah, that's what I wanted to cover. Thanks.